Hello everybody. In this video, we're going to take on the subject of powers and roots. This is where some of you who may have been doing well so far in our first 7 videos might begin to get a little queasy. Don't worry though, I'll be as gentle as I can. First, let's take a small step back to lay out some of the framework for this discussion. Let's talk about multiplication. We can think of multiplication as simply a shorthand for addition. 5 times 7 means that I am adding up 7 groups of 5 objects, or simply adding 5 to itself 7 times. That is, 5 times 7 means 5 plus 5 plus 5 plus 5 plus 5 plus 5 plus 5. Let me count them to make sure. Okay. Suppose you have 6 friends over for breakfast, and you're going to make each of them a 3-egg omelet. How many eggs do you need? 3 plus 3 plus 3 plus 3 plus 3 plus 3. You can see that a string of numbers with plus signs is not really a good way of communicating the concept of adding the same number together many times. Hence the concept of multiplication. We bring in this simple notation of 3 times 6 in place of something which is too awkward and unwieldy to be of practical value. You are probably all very comfortable with this notation, since you have been using it for a long time, and you likely don't even give it a second thought. So in the same manner that we use multiplication as a simple way of expressing the repeated addition of the same number, we use powers or exponents as a way of expressing the repeated multiplication of the same number. Say I wanted to multiply 2 by itself 5 times. Instead of saying or writing 2 times 2 times 2 times 2 times 2, I can devise a simple notation and write that as 2 to the 5th power. Let's talk a little about annotation and terminology. When I write this expression, then the number 3 is called the base. It is the number that I am multiplying by itself. The number 4 is called the exponent, power, or index. It is the number of times that I am multiplying 3 by itself. So this expression is equivalent to 3 times 3 times 3 times 3. We would generally refer to this as 3 to the 4th power. We use a special terminology when the exponent is 2 or 3. If it is a 2, then we would use this notation, and we would say that it is 4 squared. This is because the area of a square is found by multiplying the length of one side by itself. So the area of a square, which is 4 feet on one side, is 4 times 4, or 4 squared, or 16 square feet. If the exponent is 3, then we would say that this is 4 cubed. This is because you find the volume of a cube by taking the length of one side to the 3rd power. So a cube which is 4 inches on a side has a volume of 4 times 4 times 4, or 4 cubed, which is 64 cubic inches. Are we doing okay so far?
Things are going simply swimmingly.
Good. Let's move on to roots. Let's take the first 10 counting numbers and square them. We get the following results. The numbers 1, 4, 9, 16, etc. are said to be perfect squares. The inverse function of squaring a number is to find its square root. The symbol is called the radical sign, and the number inside the radical sign is called the radicand. When I say that finding the square root of a number is the inverse to squaring a number, what I mean is that when we encounter an expression like the square root of 64, we want to find the number that we had to square in order to get 64. I can look at this list of perfect squares and find 64. So the square root of 64 is 8, since 8 squared is 64. Let's try a couple more. What is the square root of 25? It is 5, since 5 times 5, that is 5 squared, is 25. What is the square root of 49? It is 7, since 7 squared is 49. We can also take the first 10 counting numbers and come up with the cubes of each of them. We get 1, 8, 27, etc. These are called perfect cubes. The inverse function of cubing something is to take the cubed root. We use the same radical symbol, and we have a radicand, but we put an index of 3 in the radical symbol to show that it is the cubed root we are looking for, and not the square root. So the cubed root of 64 is 4, since 4 cubed is 64. The cubed root of 125 is 5, since 5 cubed is 125. Are you starting to understand how this works?
Absolutely, young man.
Good. Let's work a few more problems. What is 5 to the 4th power? It is 5 times 5 times 5 times 5, which is 625. What is the 4th root of 625? It is 5. What is 2 to the 6th power? It's 2 times 2 times 2 times 2 times 2 times 2, which is 64. What is the 6th root of 64? It is 2. When I was in middle school, I struggled with powers and roots, so I did what I think probably many of us do. I scraped by without really understanding it, and then hoped that I would never have to deal with it again in my life. Unfortunately, that didn't go well. Engineering, construction, statistics, physics, computer science, and probability all use powers and roots extensively. I ended up going back to arithmetic and relearning this topic. I want to talk a little bit about something called exponential growth, since this is a direct offshoot of what we have been discussing. Exponential growth is where the magnitude of something is increasing at an increasing rate, and that increasing rate can be expressed as an exponent. I don't normally bring up this topic at this point, but I'm making an exception. I'm creating these videos during the COVID-19 pandemic. Viruses infect populations at an exponential growth rate. It is difficult to talk about the coronavirus in a pre-college math video because the topic is complex, but I can give you a theoretical example of exponential growth that I think might interest you. First, do we have a volunteer who can help me out?
Yeah, right here.
Good. Who are you, sir?
Sam. My friends call me Sammy the Shark.
Sammy the Shark. Interesting name. What do you do for a living, Sammy?
I facilitate the enjoyment of games of chance.
You facilitate the enjoyment of games of chance. You're a bookie, right?
There's them that say that, but you didn't hear it from me.
Okay, Sammy, let's see how you do with this scenario. Suppose I wanted some help in producing these videos, so I offered you a job which will last for exactly 30 days. I offer you one of 2 different payment options. I will either pay you the rather generous salary of $10,000 per day, or I will make you a strange offer. The second offer is that I would pay you a penny for the first day, then each day I would double the wages of your previous day. So for day 2 you would earn 2 cents, for day 3 you would earn 4 cents, etc.
This sounds like a serious no-brainer.
Well, let me finish. There is one other rule for this hypothetical scenario. I am requiring you to work the entire 30 days. If you quit early, you get nothing. You will only get paid after you complete the full 30 days.
Understood.
Okay, so which pay structure works best? $10,000 per day? Or a penny on the first day but doubling every day for 30 days?
As I said, no-brainer. Nobody understands numbers like Sammy the Shark.
So I just want to make sure you're taking the first option, the $10,000 a day?
10 large a day is 300 large for the whole month. No way the second option is even going to come close.
Okay, fair enough. By the way, the first option is called linear growth. Your daily salary is constant at $10,000, and the amount of money you have accumulated each day increases by a constant amount, also $10,000. We will learn in later lessons that if you graphed this result of dollars earned compared to days worked, it would be a straight line, hence the term linear growth. The calculation of the second pay option is more difficult. Let's make a chart and do the calculation by hand for the first 7 days, at least. I'll put a column for the number of days, the salary for that day, and the total salary earned to date. On the 7th day, we will have earned a total of 64 cents, and that, together with the total amount of money we earned for the first 6 days, would equal $1.27. If you choose this option, you are quite far behind the $70,000 you would have earned from option 1. So far, it looks like your option of taking the $10,000 a day is doing pretty well.
Of course. Nobody but a chump would take the second option, and Sammy the Shark ain't no chump.
If I continue to do the calculations by hand for the whole 30 days, it's going to start giving us some ugly numbers, and the chances of making an error are going to be pretty high. But I noticed that the cumulative wages can be found by taking 2 raised to the power equal to the number of days worked and then subtracting 1 penny. That gives me the number of pennies that I have earned to date, which I can convert to dollars. So I'm going to make use of the relationship and write an equation that is going to make things faster and more reliable. I can write the following equation. Total earned in pennies, let's call it T, equals 2 to the power of n, where n is the number of days worked. And then, when I've evaluated that expression, I subtract 1 cent. The fact that the growth of wages is based on an exponential function is what makes this exponential growth. In order to find out how much I earned after 15 days, I put the number 15 into the equation in place of n, and then use my calculator to solve the problem. I get 32,767 pennies, which is equal to $327.67. We are halfway through our month, and this option is far, far behind the $150,000 you would have earned at this point using option 1.
Mama didn't raise no fools. Any of you guys who didn't listen to Sammy are going to regret it.
But something very interesting begins to happen after the 15th day. By day 21, you finally have a day where you've earned about $10,000 and your total earnings are $20,971.51. That's almost $190,000 behind option 1. 9 more days to go. How are you doing, Sammy?
I don't know. I'm starting to feel a little bit uneasy. Something is happening here.
Let's go a little bit further. Let's look at day 24. The total earnings for option 2 are $167,772.15. That's a little over $70,000 behind option 1. Day 25 gives us $335,554.31 for option 2. That's $35,000 more than the option 1 people will earn by the end of the month.
I think I'm going to be sick.
Are you okay, Sammy? By day 28, option 2 wage earners have earned almost $2.7 million. By day 30, they have earned over $10 million. What do you think, Sammy? Exponential growth always reaches a point where it becomes significant, no matter how slowly it starts out. This is because the rate of increase is not constant, as in linear growth. The rate of increase is itself always increasing, or, as we generally say, it is accelerating. Calculus, which was originally invented to study objects moving under the force of gravity, studies exponential growth, since the velocity of an object falling to Earth accelerates under the influence of Earth's gravity. I'm not sure if Sammy's still with us, but I wanted to bring up one more point. As I often do, when I introduce a topic, I use simple numbers, usually counting numbers, to illustrate the point. It just makes things easier. But the application of exponents and roots is not restricted to integers. We can use any real numbers. I can, for instance, take 2.5 and raise it to the third power. This would be 2.5 times 2.5 times 2.5. The math gets a little ugly, but the concept is the same. I can do this calculation by hand, but it would take a minute or two. I can also evaluate an expression where the power is a non-integer. For instance, 3 raised to the 2.5 power. The study of logarithms is the branch of mathematics that evaluates powers when the base and exponent are not simple integers. These calculations are very ugly, and from a practical standpoint, are not done by hand. Rather, we use calculators which have the capability of handling logarithms and exponents. So with the possible exception of Sammy, we have made it through the introduction to powers and roots. There are some rules and principles associated with powers and roots that we will cover in a future video. But the principal reason I wanted to introduce you to these concepts now is so that we can tackle fractions. We will do that in video number 10, right after we cover one more preliminary topic. Thank you, and have a good day, everyone.
Have a good day, you guys.
Glad to see you're still with us, Sammy.
We hope to see you at Veterans Upward Bound very soon, and recommend a friend.